Let's implement a binary heap in Haskell. What is a binary heap? A binary heap is defined as binary tree with two additional constraints. The first constraint is a shape property. A binary heap is a complete binary tree. And the second constraint, it's a heap property. This means that the case stored in each node is greater or equal than all of its children. And of course, this property holds for every node. I will use some helper functions here, which are already implemented. This is a simple function. The first is a complete binary tree builder, which takes some complete binary tree which stored in a list and transform it to a binary tree of this type. Okay. This type battery or polymorphic data type is defined like this. So it defined in this module pretty tree, which allows me to print binary tree in console in a nice way. So, for example, I can take some list which defines a complete binary tree, for example, this list, and transfer it to this type, and then I can use this type to print the binary tree. And you can see this is a complete binary tree stored in this list, and I represent it here. Now also I have this swap function which is do swapping of some elements in a list. For example, I can swap first and third element in this list, and you can see that the element with index 1, this is 2, is swapped with the element with index 3, this is 4. Okay, we start from 0, and so we get this swap list here. Because we have this first constraint on the shape of the binary tree, this is a complete binary tree constraint. This means that we can use a list to store our binary heap. So, and we can expand our list by adding elements into the end of this list. But when we do this, we need to do some rebalancing of the tree. What I mean by rebalancing? Let's remember, first of all, how we define the left child in our array of the tree. So, to define the left child, we need to have the index child of the index of our root, and we need to multiply it by 2. And to define the right child, we also add 1 to it, like this. So I can represent the tree with one element as like this, for example. So this is a list with one element, but then I can expand this list. So I can add, for example, 2 here. So I add 2 at the end of the list, but now the property of a heap is broken and I need to do the rebalance. And I will do this rebalance by the exchanging these elements. So I need swap first and the second elements, and I need to transfer this list to this list. Okay, and this that I mean by rebalancing. Then I inserted a note in the end. And of course, I can do some. The rebalancing is done into several, can be done into several steps. For example, if I have this tree and I add 3 here, this means that I need to change the 3 with the 2. And then if I add 4 here, okay, I also need to change it at the first step. I need to change it with, so at the first step I need to change it with its parent. It's the parent of 4 is 1, because the right child of 1 is 4. So we take index of 1, this is 2, multiplied it by 2, and they will receive the index of 4. And then we need to swap them, because 4 is greater than its parent. And this transfer our list to list like this. And after that, they need to, we have the broken property in the 4 element, because its parent is less than it, and they need to swap the 4 with 3, and this give to us the correct binary heap. So let's do this iteration process of swapping elements in to implement this in our Haskell code. So I will copy this example here, and now let's define our function. So I will create one function, I will call it ins, which takes some triple. So the first element of this triple is a list of some type A. The second element is a pointer of the current node in this list of that type A. This list represents our binary heap. And the last element will tell me when to stop this iteration. So, and this function transfer all this state to the same state. So this is just transferring by swapping, which I do in this example. And also I need to have a port property to the A, or constraint. I found this nice animation which will tell us what we going to do to give us some intuition about it. So let's check. For example, here they have complete binary tree, and they go into insert 6 to it. So I do this, and we can see that we do only one swap. And now if I insert this 6 here, where is no swaps, because its parent is equal to it. And what if we insert 1 here? So you can see that they do several swaps until the end, until the root to their node goes to the root. And exactly the same thing they're going to implement now. And now let's start from the simple case. Then the have our insert function, which takes some list, and the current element is 1. This means that they go to the root, and we doesn't need to change everything. We just need to return this list and our flag that we done. So when they done, then they doesn't need any steps. I will return true here. But what if they have some list and some current element I, and no matter what the flag is? So here they have some cases. Okay, if our element, if our parent element, the parent element is stored in our list, of course, and I will define this pi. By this name, I will define this name later. This will be the index of the parent element. So, if I get this element and compare it with our current element with index I underscored, because here we will mark our nodes from 1, but in the list they start from 0, and I need then to somehow transform this I to the list indexes. So if they have such case, if our parent is greater than our current element, this means that we need to return our list as it is without doing any transformation. So we mark this here by our true, third parameter as true. But otherwise, we need to swap. So if our parent will be less than our current element, we need to swap the parent element and our current element. We do this swapping in our list. And of course we return some triple here, and the second element of this triple is parent, the parent index. This happens because we take our node and move it to the top, and then we need also at the second step take this take our node and compare it to the lead parent, and so on until we go to the root. So this is exactly what the animation showed to us. Okay, and the return false here. This means that we need to do some further processing. Okay. Now let's define our indexes, which I used here. So the first thing we need to find our parent index, and how we defined our parent index from these formulas. So if you can see here that our index can be either the even, either the odd, and having this, we can using these formulas calculate our parent index. So if our index is odd, This means that we need to calculate our index from this formula. We have parent index here and our right child defined like this. And from here we can define our parent index. Sorry, our parent index will be here and right child will be here. So, and we define our parent index like this. We need to subtract 1 from our right child and divide it by 2. Okay? Yes, I think this is correct. And let's write this. So we take our I minus 1 and divide by 2. And we will receive our parent index of our current element because it is a right child and we use right child formula. Otherwise, we use this formula, and from here we can say that our parent index is calculating like this. So we need just to take our I and divide it by 2. Okay. And of course we need to define the indexes in the list. For our current indexes will be just I minus 1 because list start from 0, and for our parent index in the list will be parent index minus 1. Okay, I think like this, and I think this should work. Let's try to check this. I will reload my module. It's reloaded, and now let's try to do some insertions. So if I have some list with one element, so I put only the first element to our heap, and I provide its index and some false here, which tells me that I need to do some iterations. So, and you can see that our iteration process doesn't do any changes in this list, just return me this list as it is and mark me that okay, we can stop. But what if I put some element here in the end, like 2, and provide its index here? So you can see that our 2 is swapped to the 1. This means that this process do rebalancing, some rebalancing, okay? And what if I at the next step, for example, what if I have this balanced tree and add 3 here and provide its index 3? You can see that it also do me this rebalancing. And so on. I can add some elements to the end and do one step of rebalancing. Let's add some more elements. For example, what if I start with this binary heap given from this step and add 4 here and provide its index and run. So you can see that we do this swap with 1 and 4, and we have this index 2 here. This means that I need do our insertion again, iterated. And in this case, I here we do one additional swap, and we receive this index, parent index, as 1. We come to the root and all swaps done, and this is correct binary heap. Okay, and actually we can use this ins function with iterate function. Let's look at the iterate function's type signature. You can see that we can use it here. And for example, how can we use it? Let's take this case and run our iterate with our ins function and with this started parameter. And of course, it will give us the infinite list. But I don't need the infinite list. I only need some part of the list. For example, let's take 2 iterations from it. Okay, and let's take 3 iterations from it. You can see that we do all our swaps and come to our final case. So if I take 4 iterations, you can see that we come to our final step, and we have this marker here which tell us about this, and we have correct binary heap. So having this, we can write our heap insert function. It takes some list which represents our tree. It takes some element which we want to insert into the end of this complete binary tree, and we will return a new tree which will represent our binary heap. So let's write implementation. We have some list here, some element A here, and of course we need to run our iteration process with our ins function, and we need to provide the initial triple. So with initial triple we can do this. We take our initial list, add to the end of this list our element A, and then we provide the index of this element. This means that we need to take our length of our list and add 1 to it, because we add 1 element, and of course we need to provide this flag which tell us that we need to do some process, more steps. Okay, now we have this infinite list, and we need to find in this list the first element where the last element of the tuple is equal to true. And we can use find function, which takes some predicate. Okay, let's see, it's type signature. It takes some predicate, some list, and returns maybe a. So the element found by this predicate. So let's create with this predicate this simple lambda function which and pattern match our triple. We need this last parameter and we just need to return it. So if it is true, our find pro function will stop at this point. Okay. And now the last thing we need to, first of all, we need to extract our value from maybe from just function. Our process will always stop, and we can use this from just function because we doesn't have nothing here returned by the find. It will never happens. And we need to take the third element, and to extract this third element we need to extract the first element. For this we will use some helper function first free, and I will define this function like this. It is a simple function which just pattern match our triple and return the first element of it. Okay, now let's try to compile this thing. Okay, problems from just first. Sorry, I need to have a step free here. Variable not scope from just. I think I need the data maybe here. Import data maybe. Let's reload. Inst. Okay, here I think I need to add some constraint because we need to compare our elements, and it's done. Now let's try to how our insertion works. I will start from empty list and add some element to it. Okay, you can see that we received this binary heap. It has only one element, nothing interesting here. But what if I want to add some elements, some more elements? Here I can use our the function and insert 2. Oops. Let's remove this $sign from here. And you can see that I have this binary heap. And I think I can use folder function to add many elements to our heap. So our folder function looks like this, but also we have fold-l function which look like this, and this is that we can use. This is how our type signature of our function, insertion function, looks like. It can be used with fold L, and now let's try to use it. Fold L hash insert, and we need to provide initial element. This is the empty list, and we need to provide the list with our elements 1, 2, 3, for example, and so on. And if I run this thing, I will get the heap. So from random list of elements, I will get a correct heap. Let's try to check this. Yes, I think this works. Let's try to... Okay, we have this function complete binary tree to the transform the function which transform the complete binary tree represent the list to a binary tree, and we can then print this list, okay, to see that all the properties hold. So I think I need to write some helper here. I will call it set, and it takes some list and transfer it to battery. And what it do, it's take this tree and just use ZB with index. It start from the root, and we provide our tree. Actually, this is the list. Let's try to load this thing. Battery of type A, of course. Yes, yes. Now I can build our heap like this and transfer it to a tree. Okay. And now I can print this tree. Yes, you can see that this is a binary heap. Okay. I build it from this list. And I can, of course, I can expand this thing. So you can see that I add 6 here, and it goes to the top. All elements are rebalanced. And this is also current binary heap, and so on. And now let's take this expression from here and write some helper function which builds from list. Build from list. Of course, it takes some list and use these helpers to build a heap. Okay. Try to reload, and you can use this build from list, and then we can print it. Yes, of course, I can write elements in any order here. For example, 7, 3, 4, 3, 2, 1, 5, 6, and I will always, at the end, it will always give me a correct binary heap. So guys, I think this is all for today. Thank you for watching. In the next video we will implement the heapify function, and extraction of the maximum element from the binary heap. And for today it's all. Thanks, push like, push subscribe, write comments, and see you in the next video. Bye bye.